Okay, I'm going to do a work energy example, and I just made it up. Okay, so here's the problem. We have the moon, and we have the lunar lander. And instead of using rockets, I want to use a big spring. So I'm going to have my lunar lander starting from rest, which isn't right, but we'll talk about that later. And it's going to fall from 1,000 meters above the surface. It's going to fall down and land on the surface. And actually, I want the spring to compress 2 meters. So I want to find out what the spring constant would be. So it falls and it compresses the spring when it lands 2 meters. Okay. Which is going to be a bad idea. But it's a good idea for physics. Okay. So I've written down some stuff that you might not be able to see very well, but I have the mass of the moon, the radius of the moon, the mass of the lander, 1,000 kilograms. Okay. It's a work energy problem because why? Yep. Because we don't care about time. We only care about the position of this here and the position of this here. We don't care about time, so that's why we do a work energy problem. Also, we're dealing with non-constant forces. The gravitational force is changing. The spring is changing. So it's best to do it that way. Okay, what's the first? We're going to say work equals change in energy. And when we write that down, the first thing we should say after that is system. I can't talk about the work and the change in energy unless I first say what my system is to do the work with. Okay, so in this case, my system is going to be the moon, the lander, plus the spring. By having all of these in my system, by having the lander in my system, I can have kinetic energy. By having the moon and the lander, I have gravitational potential energy. If I just have one of those, I can't have potential energy. And then by having spring, I have spring potential energy. So now, if that's the case, and that's my system, what forces are doing work on it? Well, there's nothing. Nothing's doing work on it. So my work would be 0. Work equals 0. That's going to be the change in kinetic plus the change in gravitational potential energy plus the change in spring potential energy. I saw a lot of this. I saw a lot of people in the assessment say, oh, well, I'll just skip all that and just say E initial equals E final. Okay, that would be true in this case. That the total kinetic plus potential would be the final kinetic plus potential. But only because there's no external work. I think this is not the best way to approach it. I wouldn't get in the habit of saying energy is final is equal to energy initial. I don't know, I would rather start from this. Okay. So it turns out to be true, but let's not do that. Okay, so now let's pick this as 1 and then down here as 2. So what's my kinetic energy at the top? So I have 0 equals K2 minus K1 plus UG2 minus UG1 plus US2 minus US1, so it's spring potential. Okay. So hopefully the final kinetic energy is 0. It ends at rest. And also for the initial kinetic energy. So both of these are 0 because it starts at rest and ends at rest. This is going to have potential in both cases, so I'm not going to let that go. Here, it's going to end up with spring potential energy, but it starts off and the spring's not compressed or stretched at all. So this is going to be 0. So now I have 0 equals UG2 minus UG1 plus US2. So now I can put in my values for the potentials and then solve for it. I don't know. So here I get 0 equals the final potential energy is going to be negative G mass of the moon, mass of the lander over the radius of the moon. Right? It ends up at the surface of the moon. And this one's going to be minus a minus, so plus G mass of the moon, mass of the lander over radius of the moon plus H. Okay. Notice that I'm using the real form of gravity. Don't use mgy. That assumes 2 things. That assumes 1, you're on Earth, and 2, that the gravitational force is constant. So over 1,000 meters, it might be constant, but this is definitely going to work. Okay, so let's just do it this way. And then the final spring potential energy is going to be 1/2 k s squared, where s is going to be equal to 2 meters. So I know everything in this equation except for k, so I can solve for k. Okay, so let's put that up here. I'll put 1/2 k s squared equals, move that to the other side, g m ml over r moon minus g ml over r moon plus h, and then I can multiply both sides by 2 divided by s squared, and I get k equals 2g ml over s squared times 1 over rm minus 1 over rm plus h. Okay, let's just check. Spring constant should be positive, right? Okay, so these numbers are all positive. This is going to be 1 over the radius of the moon minus 1 over the radius of the moon plus h. So this number is going to be a little bit smaller than that one, so this is going to be positive. Okay, so when I put all this stuff in, I should get a positive number. Now, I'm going to put it in, but I have it on my calculator right there. So I'm just going to go down there, I'm going to keep talking, I'm going to type it on my computer so that you can still hear me. Okay, let's see if I can do this real quickly. I'm opening up my calculator. I guess I should have done this beforehand, but I don't know why I didn't. Okay, so G equals 6.67 times 10 to the negative 11th. Mass of the moon is, what did I say? 7.3 times 10 to the 23rd, 22nd. Mass of the lander is 1,000. S is 2. Radius of the moon is 1.74 E6, and H is 1,000. Okay, so now I can put all this stuff in. K equals G, 2 times G times mass of the moon times mass of the lander divided by, let's put this in parentheses, divided by S squared times 1 divided by the radius of the moon minus 1 divided by the radius of the moon plus h. Print k. Okay, let's see if I did this right. I get a value of, 8 times 10 to the 5th. Newtons per meter. Okay, so that's a serious spring. You wouldn't want to do this. But then here's something you can check. Why don't you want to do this? Because go back over here. Find the average acceleration as it's stopping, going from the speed right before it compresses the spring to 0. And I suspect that the acceleration is super high. Not positive, because I don't know how fast you're going, but it's probably pretty high. 2, if you want an even more challenging problem, this is unrealistic. Because actually, the lunar lander starts in orbit. So calculate the orbital speed and then find out the energy, the spring constant, in order to stop it from both orbiting and landing. It's a little challenge for you. Or work backwards. What kind of spring would you need to launch it so it gets into orbit with the right speed? Okay, so that's a little work energy problem for you.